All right. All right. So before I continue going into my discussion in kinematics and go a little bit further, I kind of want to just make sure that I cover the bases with how what vectors are and how they work in a two-dimensional sense. So in this case, we'll be looking make it a little bit bigger. Looking at vectors. In 2D. Right? And basically, a vector is a quantity that's described by its magnitude, or a magnitude, and a direction. By magnitude and direction. So usually the opposite, or the sort of other type of quantity that we have, is what's called a scalar. And a scalar is basically a quantity that's uniquely described by one number. Examples of scalars are temperature, speed, right? Because temperature is in degrees Fahrenheit or Celsius, but it's only described by one number. You don't need an additional number or value to sort of look at direction. If it's 10 degrees Fahrenheit, it's always 10 degrees Fahrenheit. It doesn't matter what direction you're looking at. And speed as well. Speed is a scalar, and there's other things that are scalars as well, like distance. Distance is a scalar, right? But vectors are quantities that require two pieces of information. The magnitude, right, which is sort of what a scalar has, is like the only thing that describes a scalar is a magnitude. But vectors also require an understanding of direction. For example, some vectors include velocity, acceleration, force, and there's plenty of more. But basically, these quantities, what makes them different from these quantities is that these quantities require both a magnitude and a specified direction. So you'd have to look at them also in terms of like north, south, east, and west, not just simply what their magnitude is. And when we sort of draw vectors in two dimensions, here's some space over here. When we draw vectors in two dimensions, we usually sort of we look at it on a Cartesian coordinate. Right? This would be x, that's y, our x and y axes. And let's just say we had some vector, some sort of quantity. Well, it's not just purely a quantity, but let's say we have this vector and we call this vector v. And often vectors have this sort of arrow on top of them. That's sort of the notation for vectors. Oftentimes in textbooks, they'll be written just in boldface print. But in this case, I don't have a great way of differentiating that with boldface, so usually when vectors are handwritten, they're represented with an arrow on top. So this vector has a magnitude which in the schematical case is represented by the length of the vector. And you can scale that however you want it based on your efficiency. So for example, if you were representing velocity and you wanted 1 meter per second to be scalable to like 1 centimeter, then you could do that and you could draw your vector appropriately. But in this case, the length of the vector represents the magnitude. It's directly correlated or directly represents what magnitude we need. But then there's also a direction component to this because it's pointed in a certain direction. That's why the vector itself is an arrow. And we can specify the direction by specifying the angle that the object is pointing at that is elevated with respect to either the y or the x-axis. Usually in these simple cases we sort of look at it from the point of view of the x-axis. So this angle of elevation would be called theta, or sometimes we can call it anything. We can call it phi or whatever signals we want to use, but in this case we'll just use theta. And this vector is comprised of multiple components. In this case, since it's a two-dimensional vector, it's comprised of 2 components. A vertical component and a horizontal component. The horizontal component can also be from this side. Now, this vertical component we would call v of y. The components themselves are not vectors, they're just numbers, right? So in this case we have v of y, and here we have v of x. This is the x component. And with regards to this angle, the y component is represented as the magnitude of the vector, which we can simply just write as v. We wouldn't need an arrow or anything because it's just the magnitude. And it's v times sine of theta. And the x component can be written as v, the magnitude, times cosine of theta. So if you look at this, this looks kind of like the Pythagorean theorem that you learn in algebra. Because with these components, if you do vx squared plus vy squared, you're going to get the component, the magnitude of the vector. Right? And if you do the square root of vx squared plus vy squared, you'll get the magnitude. This is what's called the magnitude. If this were velocity, that magnitude would be the meters per second that is represented by this length of a vector. And if it were acceleration, it would be the meters per second squared, the numerical value. But if we want to find theta, the direction, let's say we didn't know it, but we knew it was in some sort of direction with respect to the x-axis, the tangent of theta is equal to the y component divided by the x component. So therefore, if you want to find the angle that this thing is pointed at, and depending on what the x and the y components are, they will point in different directions. And usually when we look at this angle, we try to make sure that we're looking at it with respect to the x-axis, but you can look at it from the y-axis as well, but then you would have to adjust your formulas to make sure that you're doing the right thing. I'm assuming that we understand basic algebra, and how to do the cosine and sine and SOHCAHTOA and all those things. I don't want to go too into depth with SOHCAHTOA. But in this case, the angle, which represents the direction in which the vector is pointed at, or like if it represents motion, it's the direction in which that vector is moving. We can say that it's the arctangent of the y component divided by the x component. So this is the direction. And these are the two pieces of information that go into describing a vector. If you know the magnitude of a vector and you know the direction of the vector, you basically know everything that you'll need to know about the vector. So I also quickly want to introduce this idea of how to sort of write out a vector in vector form. So how to take this vector and write out the proper vector form. So when we look at these vectors in two-dimensional space, we have what are called unit vectors. And unit vectors are vectors that go along the axes, and they basically are, if you know what a unit circle is, it's basically the points on the x and the y axis that are equal to 1, right? So the unit vector along the x-axis, which is represented as I with a hat over it, essentially represents 1. But in our vector notation, we use this, and I'll show you how in a second, to sort of represent that this is the x component. And this j with a hat on it, we use it, once again, it's basically, numerically it's equivalent to y is equal to 1. But we use it to represent that we're going in this direction, in the y direction. And if I get an eraser here, let's see, what do I want to get rid of? I'll just clear some space up here. If I want to write this vector out, this vector v, in full vector form, we would write v of x times I, which is basically it's 1, right? It doesn't change what this is. All this does is sort of signify to us notation-wise that we're in the x direction and that this component is along the x direction. And that it would be that plus v of y times j. Now this is just vector notation. Vector notation. So this basically just is a way to write out the vector. And this has its purposes too. I'll show you that in a moment. But this basically lays out like the x component of the vectors here with this unit vector along the x-axis, and this y component is here with this along the y-axis. So now this sort of leads into a discussion about the sort of mathematical operations that you can perform with vectors and how you perform those operations. So let me erase over here. All right, so this is our vector notation. And if we took, let's say we drew our Cartesian coordinate again, coordinate system, like this, and we drew something like this. Let's just say we had two vectors on it. One vector we'll call A, and the other vector we'll call B. We'll we'll call this one A. And in this arrow notation, I'll show you another notation, another way of drawing these vectors. But in this case, we're going to look at the addition of vectors. Addition of vectors. Let me just write that out a little bit better. Write out the word addition more legibly. Addition. The addition of these vectors. In this case, we're going to have this vector A and this vector B. And in this case, like I told you before, that any vector can be represented as basically an arrow in the Cartesian coordinate space that basically points in any direction that we want it to. And in this case, we have this one vector A and this other vector B, and we'd like to add them up. So one way that you can represent this graphically, like I said, there's a lot of scaling you can do with lengths and so forth, and then you can also represent the direction of the vector by the angle at which it's elevated from the x-axis, and therefore you can have a very full description of the vector, which is the magnitude and direction. But when we're adding vectors of different varying lengths and directions, we have a couple of ways that we can represent this graphically. One is this way, where we have an arrow going to its head over here, and then the tail of the next arrow is connected, or the next vector is connected to the head of the original one, and it's drawn in whatever motion or direction it'll move. And in this case, we're doing vector A plus vector B, and the result will be a vector which we'll call C. And this vector C would be this vector. It basically starts from the beginning of A to the end of this B thing. So it basically represents, which this would be a term that I had used earlier, the displacement. Basically the distance between where I started and where I ended. And there's going to be what's called a resultant magnitude and a resultant direction in this case. But for now, I'll just show this graphically. You can also represent a vector similar to this by, let's say this was our vector A, by connecting the two tails and allowing the vectors to extend as they normally will, and then just allowing from this point to extend vector C. Let's see this. Is this good enough? Yeah, it's a little short. Okay. We'll call this a vector C. And we can see that from these two, this vector extends. And these are sort of the parallel parts, constituent parts of this bigger vector C. But we can, in both of these ways are fine. If I had drawn it like this on the Cartesian coordinate system, it would have been just as good as this, but I personally prefer this method. Something about it that makes more sense to me and I like it. So I'll just use this. And you'd probably guess that A has its own components. The A of x component along the I unit vector, right? We have I and j they're unit vectors that represent the direction that we're going in, but numerically they're just equal to 1. They're just symbolic of the direction that the vector is going in. The component is of the vector is going in. So this is a vector representation of A. And likewise, we have a vector representation of B. So if we want to add A and B, what we have to do is we have to add the x components together and get a resultant x component, which is the x component of C, and add all the y components up to get a resultant y component. And that is done like this. Right? So in order to properly add all the vectors together, we have to add all the x components of the vectors together, all the y components, right? Because all the x's are x's. So when we're adding the vectors up, the x components and the y components are treated separately, as always. So the way to properly and then what happens is that this new vector, so let's say that this vector was 2i and 3j. And then let's say this one was like 4i and 5j. Right? Well, this was 2 and this was 5. So these would add up to become like 7. And this was 2 and this was 4, right? So these would add up to become 6. And this was 3 and this was 5. So this would add up to become 8. So the new x and y components of the new vector, which this is now vector C, would be, right, what did I say? Let's say this was 2, that was 3, that's 4, and that's 5. So then these two would add up to become 6. And these two would add up to become 8. And these numbers can be numerically represented as magnitudes, which they are. It's basically saying that if this vector, for example, was like velocity, it's saying that you would be moving 2 meters per second in the x direction, but 3 meters per second in the y direction at the same time. And you'd be able to define direction that way. So if you want to find the direction of solely A, you would have angle A, I'll represent it as a subscript, is equal to the arctang of AY over AX. Right, so in this case, the direction of vector A is represented by the arctangent of the y component divided by the x component. And in this case, the direction of vector B is represented by the arctangent of this component divided by this component, the y divided by the x component. And in this case, with vector C, which we got from adding vector A and B, the direction of angle C would be the arc of a vector c would be the arctangent of cy over cx. So in this way we can sort of fully describe our vectors. And of course the magnitude would be coming from doing the Pythagorean theorem for each of these. So if we wanted to find the magnitude of this vector, we would do ax squared plus ay squared. And the same for here and here if we want to find the magnitude of these vectors.